Right, so Module 9 is looking at a topic that we actually have seen the need for this for quite some time. In many of our programs, we've printed out things like dollars and cents, and we haven't really controlled the level of significant digits that appear on the screen. So we're going to learn among significant figures, we're going to learn a few other formatting tools that are available to us within C++. And this topic is covered largely in section 4.10 in the textbook, pages 140 to 144. Again, we've skipped over a little bit of content that we're going to come right back to in a few modules, but you should be able to tie this to the textbook as well. All right, so first off, output formatting. Let's think about what the problem is. If we look at several of our programs, we've printed out many outputs in each one of them. Sometimes the outputs are one right after another, and we've spent some time entering in a whole bunch of different spaces to make individual lines start to line up, and that's neatened up our input or our output, but it's a little tedious. We've also dealt with the precision of decimal numbers. We haven't really tried to fix that just yet, and that's one of the problems that we're going to solve in this module. And we'll also start to deal with left and right justification of text, which really only comes into play once you start controlling the width of a given thing that you print out. We'll call that a field for today. So to do these things, what we're going to do is we're going to include a library. Just like we included CTime and we included CMath, now we're going to include iomanip. So it's IO manipulations. This contains what are called stream modifiers. The output, cout, it's actually, we've called it a command, but really it's a stream. It's an output stream. Streams in C++ just refer to something where you can add to one end of a stream and it's carried out to the output or the terminus of that stream. An output stream here is our program's the input part of it, the starting point of that stream. And the terminus, the end point of that stream, is things being printed out to the console. So what we're doing now is we are going to print or insert modifiers into the cout stream that are going to change how things end up being printed later on. So what's a little strange about this is that it'll appear that these new functions and these new terms that we learn are being printed, although they don't print themselves. What they do is they modify everything else. So let's look at an example. Let's say we're going to print out height separated by a space separated by time. I believe in one of the modules before this we had a program that would print out the height of an object that's going to fall and how much time it might take to fall. So let's assume those are two variables with double precision, so they're doubles, and we've got a space. Each field is formatted in C++ according to some default set of rules based on the data type. So for instance, an integer is fairly straightforward to print out. Doubles are a little bit more specific in that we will have up to 6 trailing digits print out with a double. But really the rule of thumb is that we're going to have 8 total digits. So if we've got the number 1.333 trailing threes, we'll have 1 point with 6 threes. The default representation of 10.333 would be 10, 1, 0, dot, with only just 5 trailing digits. So the total width of a double that gets printed out really is just 8. Now let's say I want to change that. Let's say I want to actually try to manipulate the total width of the field that gets printed out. And actually I look at this example and I've only got 5 trailing digits here. Let's assume that the default could change. Basically we don't have much control over it, right? So we print out height. If that ends up being an exact number, it'll just print out as 5. Time might come out as 1.010115. One way we can start to limit the amount of space that each one of these takes up, or expand the amount of space that each one of these takes up, is using the set width modifier. So the set width modifier, when we include iomanip, it almost appears that we're calling a function. And you can think of it like that. We're calling a function, but we're printing the result of this function. So cout insertion operator set width to 4. What that does is it makes sure that the very next thing that gets printed out, and only the very next thing that gets printed out, takes up 4 spaces, 4 digits on the output screen. So by default, numbers are actually right justified within their fields. When I do a set width 4 with a height, it's going to print out as 5 because it's an exact number. Even if it's 5.000, this is going to show up with 3 blank spaces followed by a 5. That one field is going to take up 4 spaces on the output console. I have my space over here, and then I'm doing set width 5. And again, the set width 5 only affects the very next thing that gets printed out. And now I can see that I've actually chopped this off, so there's only 3 levels of significant figures. Now, I don't want you to concentrate too much on significant figures with regards to set width. Set width actually works with characters. It works with any type of output data type. It's not it's not dealing with precision. It's simply dealing with the amount of character space that is going to be reserved on the output screen for that particular number or that particular output. If we want specifically to deal with precision, it's a separate operation. So there's actually a combination of 2 stream manipulators that should be used to set significant digits. The first is set precision, which gives you the option of specifying how much precision or how many significant figures you want. But the second, and should always be used, so fixed will always be used with set precision, is this fixed notation. Fixed means I want fixed floating point notation. I don't want scientific figures. I don't want scientific notation. It's important that we put the fix with set precision to ensure that our numbers always print out with the specified number of decimal places. So you can think of these almost as a pair. So set precision is a little bit different than set width in that it's not obvious from this example, but it will be when we start to code some more problems up. Set precision is considered permanent. It's a permanent stream modifier. Permanent in that until you reset it, set precision 2 would reset it, you are going to print out every double with a precision of 1. Set width is different from that, and that set width only refers to height. If you leave out the set width over here, time to fall will print out with its default width, no matter what. So let's kind of keep a running total of this. Switch over to our notes, and we want to remember that set width is a temporary modifier. So it only affects the very next field that gets printed out. Set precision and fixed are permanent. They affect all fields until we reset it. Okay, so we can reset the precision to something else. So it's very important to keep in mind those differences between those 2 classes of input modifiers. It's an easy one to forget. Now the third one that we're going to look at before we see a larger example is dealing with justification. You'll see that all 3 of these sort of work together. Justification only really is applicable when you're using set width. When you use set width, we're going to have a specifically set number of digits that are going to be reserved for a value. By default, if you allow or if you specify more digits than is required for a number, a digit, an integer, or a double, everything comes out right justified. And so if I was to actually write a program and see out with set width of 3, 1, 10, and 100, you would see it come out to the screen like this. Each line would be right justified. If I want to change that, I can do see out left, and this is another stream modifier. And I can embed left in here as well. It doesn't have to be on its own separate line. Left is like set precision and fixed in that it's permanent. Until you set it back to right, it is going to affect every subsequent field that gets printed out. So when I say left justified, now when I do set width 1, it'll appear on the left-hand side. So again, if we want to keep a running list of our stream modifiers, left and right are also permanent. They have to be reset. So set width is sort of the oddball. Set width has to be respecified before each individual field is printed. And if you don't print it, then it just uses the default. All right, so let's look at a quick example. And before even getting into this, I want to just give you a couple of pointers in terms of doing your output formatting. Output formatting is not really a science. There are typically many different combinations of justification and set width and precisions, well, not so much precisions, to get your output to look the way you want. There is no perfect way of going about this. So there is typically a little bit of trial and error using the tools that you've learned, set width, set precision, fixed, and justification to get everything the way you want. I'm going to try to point out a few tips here. So I'm going back to, this is essentially the same as programming example 8. All I've done now is I've modified the problem statement to say, let's print this stuff out nicely. For instance, let's make our interest rate print out with maybe 1 significant figure. Let's make the dollar and cents print out with 2 significant figures. And then let's have this table print out in a nice form. So if I bring up, I already ran this program, and it's exactly the way it was for example 8. When a user types in the 10,000, the 10, the 365, you can see that nothing's really nicely lined up. Maybe I would like all these numbers to be lined up on the same column. Maybe I want yearly interest rate to print out with 1 significant figure, and certainly I don't want .6. I want maybe two levels of precision there. So let's take it one step at a time here. Instead of dealing directly with the numbers first, what I'd like to do is I'd want to make all the numbers aligned. So it's sort of a nice tabular output. And in fact, let me copy this, and we can draw on it. So what I'm really looking to do is to have this left part, all these numbers, line up as a nice even set. So I'd like the 10.0%, I'd like 365, and I'd like 11051.60. Right? So let's just deal first off with getting the text and these numbers to line up nicely. So the first tip that I'll give you is that to get numbers to align up, so if you have a situation where you've got labels followed by numbers, to get all these numbers lined up along these columns, don't think of it as printing out these numbers differently. What you want to do is you want to think of it as printing out each one of these labels such that they occupy a certain width. And that certain width is really going to be the maximum width. So what I'm going to do is I'm going to change principal so it occupies more space. Right? Enough space to push this over to the right. Same thing with the yearly rate, same thing with times compounded, and the amount at the end of the year. So let's switch over to the code. And again, if you want to go back and see how we got this program written in the first place, this was programming example 8, the previous one in the previous module. I've taken it and I've copied it over, and now I'm going to start to add my input formatting. So I'm looking at this amount at end of year. This is the largest label that I have, and in fact, I'm gonna separate out the dollar because I don't want that necessarily to become part of the label. So that's really, in both cases, these are parts of the number, not the label. So I'm going to separate those out, and I'll show you the effects of those a little bit later. I'm going to look at this, and this is the largest label that I have. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and maybe 2 or 3 more. 25 seems reasonable, right? So what I'm going to do is I'm going to make each one of these labels have a set width, or a width, of 25. I'm going to include my iomanip. And I'm going to put a set width of 25 in front of this. So let's print that out. So I got my 10,000, I got my 10. Oops, went a little too early. Visual Studio had not finished building. Okay, there we go. Let's rerun this. So I got my 10,000, my 10% interest. I've got 365 days a week. Okay, so we see the principal has been shifted over. It occupies a total of 30 spaces, or 25 spaces. But of course, it's right justified, right? So we want to avoid the right justification. Notice that if we apply this to all the rest, we're going to end up with these numbers matching up. So let's do that first before we actually do the justification. Set width is not permanent. It has to be restated before each thing that you want to be of width 25. So I'm going to make each one of my labels 25 spaces. So same inputs. Okay, so right off the bat we see, okay, this is starting to turn out correctly, right? Everything is nicely lined up along a certain column. We don't want the labels to be right justified like this, so let's change them over to left. Now what that does is it makes not only these labels left, all of them, but it also makes all of these left justified. So when I start to use, if I was to use set width with these, I'd have to remember that. Now it turns out I'm probably not going to use set width with the numbers because I don't really, they're the last thing on the line, and I don't really care how much space they take up. So let's run this one more time. And now we see that the labels and the numbers are all sort of nicely and neatly formatted. Now remember, I moved that $ out, right? Now if I didn't do that, if I just did this instead, this is my original line of code that I had. I had the $ as the last thing part of the label. The reason that doesn't look very good, if we run this again now, is now the 30 or the 25 width, I don't know why I keep saying 30, the 25 width is applying to all of this. So the $ is right where it would be when you printed it out, right here, 2 spaces to the right of the colon, and then there's there's a remaining amount of trailing space. So the separation out of that $ is important because it makes the $ not affected by the set width. It's only this principal part that's part of the set width now. All right, so now I've got to go back and deal with my precisions. So the only things that have precision issues is this percentage and my dollars and cents. Set precision 1 will take care of that, and set precision 2 will take care of this. And then we just need to make sure we call set precision before we print out that, and set precision before we print out the percent to make this work. So normally, my permanent modifiers I like to do on separate lines. It's not required. So before I print out yearly rate, I'm going to do cout set precision at 1. I'm also going to do up here, and I could do it right at the same time. I could do fixed here. Fixed, I want everything in fixed in general, so let's just do cout fixed up here first. Remember, fixed goes hand in hand with set precision. It doesn't really matter which order they're doing, but they're both flags that control precision. My set precision 1 will affect technically yearly rate, but yearly rate's not a number, so it doesn't do anything to it. It'll affect yearly rate, it'll affect times compounded, and amount at this point. So if I type in the same numbers, I see that my decimal place comes out at 0. One decimal place for yearly rate. Times compounded is an integer, so it always ends up at 365. There's no issue with that. Of course, this is still 1 precision. Now notice that we now, instead of our 10,000, we get 10,000.000. That's because of the explicit fixed. All right, this is forcing C++ to print out all decimal values as fixed point notation. The default is to sort of be smart about it. To remove that, if I remove that fixed point, principal will print out as 10,000 if it's exact, and if it's not exact, it'll add more digits. By saying fixed, I'm forcing everything to be a certain number of digits. Now, principal really should have been 2 as well, and I missed that when I was doing our diagram here. Really, I should have had a dot 0, 0, and the set precision 2 would have affected that as well. So let's add that. We'll do set precision 2, cout set precision 2. We'll print out the principal. We'll set precision to 1. We'll print out the yearly rate, and then we'll set the precision back to 2 before printing out the amount at the end of the year. One more time here. And now we've got nice dollars and cents as the principal. We've got an interest rate with one significant figure. I don't know whether that's necessarily the best way to represent interest rates, but it's pretty common. And the amount at the end of the year. And it doesn't matter what we type in, right? So if the user types in $4.56.89, which is nonsense, and as an interest rate, maybe 20%, 0.638 as an interest rate, let's say once a year. We still print out 4.57 because we've printed the principal with 2 levels of precision. And notice it rounds, right? It's not a chop off like an integer division type thing. It really does smartly round. The interest rate is always printed out with 1 level of significant figures, so the 20.638 ends up as 20.6. Of course, if you add 20% interest rate, you'd make a pretty good amount of money off your $4.50. You'd have a little less than $1 added to it, and so you see the actual amount at the end of the year, and again formatted for decimal places or for dollars and cents. So this is just one example. We'll use I/O manipulation quite a bit throughout the rest of the modules. Sometimes we'll write some programs that maybe could use it, and I'll leave that as an exercise. It takes some practice to get used to using set width and set precision. The key thing to remember is the diagrams or the listings that we had earlier. Remember that set width only affects the very next thing that you print out. I have to keep repeating set width 25 because it'll only affect this individual string. Set precision will affect everything until I reset it. So keep those distinctions in mind. All right, so Lab 4 is all about kind of putting together a number of things that we've done over the last few modules. It's gonna involve using the power function, and it's also going to require you to do some output formatting. So I want you to calculate the monthly payment on a loan using the following formula. So I've got the interest rate, the number of times you pay per year, and the amount of the loan. And so I've given you some details about the different parameters from the user, certainly the original amount of loan, the number of payments. So if the user is going to say that I'm going to pay, if the loan term is 1 year, I'm going to assume that there's a monthly rate. So sorry, I kind of misstated N here. If it's a 1 year loan, N would be 12. You're paying 12 payments, 12 monthly payments. If the loan is 5 years, N would be 60. And you're going to have to explain to the user how to enter this in. 60 meaning 60 total monthly payments. The rate is a monthly interest rate in our formula, but pay attention to this. I want the user to type in a yearly, an annual interest rate. That's the way most loans are usually advertised. But keep in mind that the rate inside this formula should be whatever the user typed in divided by 12 as a monthly interest rate. So you're going to write this program that asks the user for an annual interest rate, a loan amount, and a number of payments that they will make. 60 for a 5-year loan, 72 for a 12-year loan, and on and on. Your program should compute that monthly payment and the total amount that they will pay over the lifetime of the loan. So you think about that. Once you figure out the monthly payment, simply multiply it by N. Hopefully you realize that if you've got a loan for 5 years on $10,000, you don't pay the bank back $10,000. You pay the bank $10,000 plus all the interest. Each monthly payment has a portion of monthly interest in it. So again, that's why this formula is more complicated than the loan divided by the number of payments, right? So the interest is going to increase your monthly payment. So print out the monthly payment, print out the total amount, and then also print to the user the total amount of interest that they paid, which again should be the total amount paid minus the original loan amount. The program should echo the input from the user and print out the results in a really nicely formatted way. So I gave you kind of an example of what you should try to look towards. I'd like you to format your input prompts such that all the user's inputs line up really nicely. So notice that enter your loan and annual interest rates, they all have examples. All their inputs as the user types out line up. Remember, you can't control the formatting of their input when they type this in. So you want to look at this label and assume that this label is a fixed width. Right? Each one of these labels is occupying a fixed width. Prompts, not labels. Afterwards, you're going to print it out. So again, I've got a nicely formatted printout. Our interest rate is in 2 percentage point, dollars and cents, so that made that a little easier for you. And you can see how I'm printing out the monthly payment. This is also a good test case, right? So you know that these numbers are right. Make sure that your program works against these test cases, and then try it with a number of different inputs.